A black hole the size of a coin could contain the mass of a mountain. Compress that much matter into a space smaller than your hand, and gravity becomes so strong that not even light can escape. It is a place where the rules of physics begin to break, where time behaves strangely, and where our understanding of the universe meets its limits. We cannot see inside. We can only study the effects it leaves behind. For centuries, black holes existed only in theory. Early astronomers observed stars moving in ways they could not explain. Something massive, yet invisible, must have been influencing them. It was not until the 20th century that science began to understand what these objects might be. A black hole is not a hole in space. It is an object of extreme density. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The outer layers collapse inward, and the core shrinks. If the star is large enough, this collapse continues until the core becomes incredibly small, a region where mass is concentrated in such a tiny space that gravity becomes overwhelming. This is the birth of a black hole. Gravity is the force that keeps planets in orbit and objects anchored to the ground. It is a universal attraction between masses. But black holes take gravity to an extreme. Near their surface, the gravitational pull is so strong that escape becomes impossible. The boundary around a black hole is called the event horizon. The event horizon is not a physical wall, it is a point of no return. Once crossed, every path leads inward. Light itself cannot escape. That is why black holes appear invisible. They are not objects we can see directly. We observe them through their influence on surrounding matter and radiation. It is sometimes said that black holes suck things in, as if they were cosmic vacuum cleaners. This is a misunderstanding. Gravity obeys distance. If you replace the sun with a black hole of the same mass, Earth would continue orbiting in much the same way. The danger of a black hole is not that it reaches out across space, but that its effects become extreme when you approach too closely. Another concept often associated with black holes is spaghettification. This term describes what would happen if an object approached the event horizon. Because gravity is stronger closer to the black hole, different parts of the object experience different forces. Imagine stretching dough. The object would elongate. Scientists use the term to describe differential gravitational effects, not as a dramatic image of horror. It is a natural consequence of physics in extreme conditions. Black holes challenge our understanding of space and time. Near one, time itself behaves differently. According to Einstein's theory of relativity, gravity can slow the passage of time. To an outside observer, an object approaching the event horizon would appear to slow down, its movement stretching until it seems to freeze. This is not science fiction. It is a prediction of physics, confirmed by experiments and observations. But what happens beyond the event horizon? This is where knowledge meets mystery. Inside, our current understanding of physics breaks down. At the center of a black hole lies a region called the singularity, where density becomes infinite, and the laws of nature as we know them cease to apply. Scientists debate what truly exists there. Some theories suggest exotic structures. Others propose ideas that challenge our conventional understanding of space itself. We do not yet have all the answers. This uncertainty is not a weakness of science. It is its strength. Black holes are laboratories for extreme physics. They allow us to test ideas about gravity, space, and time in ways that are impossible on Earth. Each observation brings us closer to understanding these mysterious objects. Beyond the event horizon, our understanding ends. The event horizon is the boundary of a black hole. Once crossed, nothing can return. Not matter, not information, not light. It is a point where space itself bends so severely that all paths lead inward. At the center of a black hole lies the singularity. This is a region where density becomes infinite, and the laws of physics as we know them break down. Imagine compressing all the mass of the black hole into an infinitely small point. Our equations predict strange results. But they also signal something important, that our understanding is incomplete. Scientists debate what truly exists inside. Some theories suggest exotic structures. Others propose ideas that challenge conventional notions of space and time. We cannot observe the singularity directly, and so research relies on mathematics and indirect evidence. This is not a limitation of science, but a reminder of how much remains to be discovered. Black holes are often portrayed as cosmic threats. It is true that their gravity is extreme, but black holes in space are far away. They do not roam the galaxy searching for planets to consume. Gravity obeys distance. If you approached a black hole from far away, you would feel no unusual force until you came very close. The idea of black holes sucking everything in is a misconception. Consider this. If the sun were replaced by a black hole of equal mass, Earth's orbit would remain largely unchanged. The planets would continue their paths around the center of mass. The difference is that we would lose the sun's light and warmth, not because the black hole reaches out, but because it emits no light of its own. Black holes are dark because they trap light, not because they are cosmic vacuum cleaners. Time behaves strangely near a black hole. According to Einstein's theory of relativity, gravity can slow the passage of time. Near the event horizon, time dilation becomes extreme. To an outside observer, an object approaching the boundary would appear to slow down, its movements stretching until it seems to freeze. This is not fiction. It is a consequence of how space and time are connected. Experiments and observations support these predictions. Satellites and precise clocks show that time runs slightly faster at higher altitudes on Earth, where gravity is weaker. These differences are small, but they confirm the principles that also apply near black holes. The same laws of physics govern both everyday life and the extremes of the universe. So, why do black holes matter? They shape galaxies. Supermassive black holes reside at the centers of most large galaxies, including our own. Their gravitational influence affects star formation and galactic structure. Without them, galaxies might evolve differently. Understanding black holes helps us understand the cosmos itself. They also challenge our knowledge. Black holes test theories of gravity and quantum mechanics, two pillars of modern physics that are not yet fully unified. Studying them could lead to breakthroughs in our understanding of space and time, and they inspire curiosity. Human history is defined by exploration and discovery. From the oceans to the moon, we have always sought to understand the unknown. Black holes represent one of the greatest frontiers in science. They are terrifying only because they reveal how much we still have to learn. But fear and wonder are closely linked. The night sky once inspired myths and superstitions. Today, it inspires scientific inquiry. Black holes, though extreme and mysterious, are part of the natural universe. They obey rules, even if those rules challenge our intuition. Science is the process of discovery. Each observation of a black hole brings new information. Each theory refines our understanding. We may never answer every question, but the pursuit of knowledge itself is valuable. In the end, black holes are not just objects of fear. They are reminders of the universe's complexity and beauty. They show us that nature operates on scales and in ways that stretch human imagination, and they invite us to explore, to question, and to learn. If you enjoyed this journey, consider subscribing for more explorations of the cosmos. There are countless mysteries waiting to be uncovered,